I welcome everyone into the presentation of the EE675 Introduction to Reinforcement Learning course project. Myself, Mithun Raj. I am third year undergraduate student studying in IIT Kanpur. So our paper is best term identification for cascading bandits in the fixed confidence setting. And it is being mentored by Dr. Subramanya Swami Peruru sir, and my co-presenter is Anjali. So let's go into the discussion, and this is the presentation of the paper one. So first, we need to know about the cascade best arm identification model. So we need to have some basic knowledge of some terminologies, so that we can understand this paper very easily. So the first term is that cascading bandits model. What does cascading bandits model means? It assumes that when we see a recommended list, the user evaluates the items very sequentially. So the user clicks on the item if he or she attracts to the item, or skips when he or she doesn't attract to the item. So this process continues till the user clicks on the item or all the items get exhausted. So this is cascading bandits model. So the next term is feedback. So the feedback received here is binary. Either the binary means the user clicks the item or not. So this is the binary feedback. If the user clicks the item, it's considered to be attractive. Otherwise, it's not considered to be attractive. So this is feedback. The next term comes here is the click probability. So what click probability is that each item in the ground set. So we'll be knowing about the ground set in the next slide. Each item in the ground set has an associated click probability known as W of I, which represents the likelihood of the user clicking on the item. Okay, these probabilities are unknown to the learning agent. Okay, so the term learning agent is also in the next term itself, so that you can understand. The next term is the independence. So the click probability of an item is independent of the other items. Okay, it doesn't depend on any other item, the click probability. This means that whether the user clicks on the item does not affect the probability of the other item. The next term comes here is the optimal solution. So here the optimal solution is to recommend the list of the items with highest click probabilities. So this is the optimal solution here. This maximizes the chances of the user clicking and on at least one item in the list. So this is the optimal solution. The next term is a learning agent. So the learning agent aims to learn the click probabilities of item based on the feedback received from the previous recommendations. Okay, it explores the combinatorial space of possible item, so that the optimal list is with the highest probability in a few time steps. So we need to have some highest probability in a few time steps only. Next, we go into the setting of the cascading bandits. So when we go into the setting of the cascading bandits, we need to know some terms, the setting of this. First, we'll be knowing about the ground set. So what does the ground set means? This is a set of all the available items in the list. Okay, this is the set of all the available items. Next term is click probability or weight of the item. This click probability belongs to the set of ground set. So item I attracts the user with probability W of I, and this is independent of other items. So W of I is binary. The distribution taken here is binary. If he or she likes, the click probability will be 1. If he or she doesn't like and doesn't click on that, the click probability will be 0. So whether the item is clicked at time t or not, how this is being revealed? This is being revealed by the random variable Bernoulli distribution we will be taking here. Okay. See the weight of the item is 1 if and only if the user observes and clicks on the item I at time t. Okay, and it is 0 if the user observes, but he or she doesn't click on the item. The WT of i's are only observed just for some items, but not for all the items. So we go into the next slide here. So let's take an example here so that we can understand the setting very easily. We'll be having some 9 number of fruits, L equals to 9, L equals to 9 number of fruits. So when the time steps goes on, T equals to 1 to 2, the agent select a list of K items. Okay, here we can see the agent selects K, the agent selects 5 items here. Okay, okay, the agent selects 5 items. So that we get the total number of permutations is L power K, and these all the recommendations that are being seen by the user. Okay, so next we see, so here L equals to 9 and K equals to 5. So we the recommendation list are 5. So the attractiveness and the weight will be seen now. So for the first recommendation is banana. So the user is not attracted. So WT of I is 0. Next is apple. So the same, he or she is not attracted. WT of I is 0. Next is mango. WT of I is again 0 because he or she are not attracted to that. Next comes the orange. So here the person gets attracted to it. So WT of I becomes 1. Here the process ends because he or she clicks on the item and the process stops here. So we don't know the next item is being attracted or not. Okay, so the user examines the term here. If she is attracted to an item, she clicks on it. If she is not, she skips to the next item and checks if it is attractive or not. So the process stops when he or she clicks on the item or when the list ends. So next we go into the example. So how does the user get, how does the feedback we get from the user at time t? So we define a kt tilde, which is minimum of 1 and a total number of items k, with wt of ikt is equals to 1. So if kt tilde is less than infinity, then the agent observes. So the agent observes and click, but does not click. So wt of ikt equals to 0. But wt of ik tilde t equals to 1, and he or she doesn't observe for k greater than or equals to k tilde. Okay. Next comes if k tilde equals to infinity, the agent observes and wt of ikt is equals to 0 for k between 1 and k. So this is the feedback from the user received. So we go on to the next slide. So best arm identification cascading bandits with epsilon delta k setting. This is the setting we use. So we assume that the weights W of 1 is greater than or equals to W of 2 and so on, W of L. So this is W star, and W of L is the last weight, W prime. So what is the optimal item here? What do we mean by optimal item? K is a set of all the items that belongs to L. So W weight of I is greater than or equals to weight of K. That is the optimal item here. What does the arm means? Arm means set of all the permutations of all the K items. This is arm. So what does the next optimal arm means? The whole permutations of K power K. S star is denoted as optimal arm, and square bracket of K here denotes any permutation of K. So K power K is a set of all the optical arms. So next we go on to the next slide. So here we come across a deterministic and non-anticipatory online algorithm consists of a triple set, pi t of t and t pi and phi of pi. So we'll be defining some 3 terms. How does this algorithm runs? First is sampling rule, that is denoted by pi t of t. Next is the stepping rule, t pi, and next comes the recommendation rule, phi of pi. So let's get into the first term, and this is sampling rule. So what does the sampling rule means is that which arm st of st pi to pull a time step t. So sampling rule decides that which arm to be pulled at time t. So S pi of t is ft minus 1 measurable. So then that is called ft minus 1 is known as the observation history, and ft is the sigma set of S1 pi and order 1 pi and so on to st pi and ot pi, order at time t and sampling rule pi. Next comes the stepping rule t pi. So what does the stepping rule mean? This means that when to stop, and t pi is denoted as stopping time with respect to the ft of ft, and this satisfies the probability as t pi less than plus infinity, and that equals to 1. Next comes the recommendation rule phi of pi. And what does the recommendation rule phi of pi means? Which arm the S pi to choose eventually is decided by the recommendation rule, and ft pi is measurable. Next, the term is t pi. T pi is the time complexity of the pi. Pi is the total triple set here: the sampling rule, the stepping rule, and the recommendation rule. The whole set comes under pi. Next, we go on to the next slide. So what do we mean by fixed confidence? Fixed confidence is that the risk parameter, we define some failure probability as delta, which lies between 0 and 1 and is being fixed. Okay, so this is known as the fixed confidence. So the other term is algorithm pi is delta k PAC. What does PAC mean? Probably approximately correct. So we define some algorithm, probability of weight pi, S pi that belongs to the optimal arm. K power k is the optimal arm that greater than equals to 1 minus delta. So delta is defined here as failure probability. Okay, next, what is our goal? What is our actual goal that needs to be accomplished here? So our goal is that to obtain a delta k PAC algorithm, PAC is probably approximately correct algorithm pi, such that the expectation of the time period of the time complexity is small, and the time complexity is small with high probability. So this is our main goal to achieve here. So the expectation of the time complexity should be small, and the time complexity is small with high probability. So next, what is the optimal expected time complexity over all the PAC algorithm? This is time complexity, optimal time complexity is denoted by 3 star, and the terms are epsilon delta k. And how is this defined is that infimum of the expectation of the time complexity, and pi is the set of triplet set of epsilon delta k PAC. And optimal expected time complexity measures the hardness of the problem. We go on to the next slide. So what is our actual problem here? Best arm identification. Okay, so how to identify the best arm? So given delta equals to 0, what does delta mean? The failure probability. Okay, a learning agent aims to identify an optical arm with probability 1 minus delta in minimal time steps. Okay, so this is that the learning agent needs to identify the optimal arm with probability 1 minus delta. 1 minus delta is as success probability with less number of steps. So this is the first thing. The next is that given a b greater than 0, the agent aims to maximize the probability of identifying an optimal arm in b steps. So we will be having two things here. The first is that we need to find an optimal arm in minimal time steps, and we need to maximize the probability of identifying an optimal arm. So these two kind of settings are known as fixed confidence and fixed budget settings. Okay. So under this fixed confidence setting, the work aims to identify an optimal item, and later ones aim to find an optimal arm. So fixed confidence setting, we'll be knowing about the optimal item, and the next later ones will be knowing about the optical arm. So this is about the best arm identification problem. Next, we go on to the next slide. So let's see the algorithm. How does this best arm identification algorithm works? Okay, so we just give an input. Delta is the risk, tolerance is epsilon, and size of the arm is k. So first we need to initialize. t equals to 1. D1 is the total number of items available, the set of all the items, and A1 is 5, R1 is also 5. T0, the initial time complexity will be 0, and the weight is also assigned to be 0, and for all I. So the actual algorithm begins now. While dt is not equals to 0, the total number of items not equals to 0, at will be less than k, and rt will be less than l minus k. L minus k is the total number of items, and k is the recommended items. So L minus k is the rt. So now we'll be sorting the items in the dt according to the previous observations we have been observed. So we'll be getting it as tt minus 1 I1t less than or equals to so on, and tt minus 1 it dt. So if mod of dt greater than or equals to k, then we'll be pulling arm from the set I1t and I2t so on to IKT, or else we'll be pulling the arms from the I1t, I2t to I mod dt and st prime. So what is st prime here? This is any k minus mod dt subset of at and rt. And we'll be ending if observer clicks on the item. So kt tilde is defined as the click observation, and that belongs to the set 1 to k to infinity. So for each it goes in this way. For each I belongs to dt, how do we define the weight here? Weight is defined as the t minus 1 I, the previous observation multiplied with the previous weight plus the present weight divided by the previous number of previous observations and plus 1. So tt of I is defined as is equals to tt minus 1 I plus 1, or otherwise set wt cap of I. This is the new weight equals to the previous weight only. So tt of I is equals to tt minus 1 of I. And kt equals to, what does kt mean here? K is the total number of recommended items minus mod of at is kt. So we'll be using here UCBs and LCBs. UCB is defined as ut of I comma delta is defined as the expected new weight plus ct of I comma delta, and lt of I comma delta is the new weight wt of I minus ct of I comma delta. Next, we'll be finding all the items in dt that have the kth and kt plus 1 largest empirical items. So we'll be maximizing that, and J star is the optimal thing. So at plus 1 equals to at union of I belongs to dt, and that set lt that is greater than equals to ut minus epsilon, and rt is rt union with I belongs to dt, and ut which is less than lt of j prime delta minus epsilon, and dt plus 1 is equals to dt by rt plus 1 union at plus 1. So we do t equals to t plus 1, and we end while if at equals to k, we get the output as at, otherwise output the first k items that entered a. So that we get this algorithm in this way. So some theorems are being used in this algorithm. So let's get into the theorems. The first theorem is upper bound. This is we see some special cases of the upper bound. First is that if all weights are at most 1 by k, 1 by k is the k is the total number of recommended items with probability at least 1 minus delta, then the algorithm 1 outputs S star after at most this time period. We see order of 1 by k sigma delta sigma of I power minus 2 is defined in next. So what is delta? First, let's see what is delta I. Delta I is weight of I minus weight of k plus 1 if I lies between 1 and k, and if I lies between k and L, weight is W of k minus W of I, and delta of sigma of 1 is greater than equals to delta of sigma of 2, and so on, greater than equals to delta of sigma of L. So delta is determine the hardness of the identity item, to identify item, sorry. So how easily or how we can find the item is being determined by delta I. So if all the WIs are at most 1 by k with probability of at least 1 minus delta, then the algorithm takes these many steps. Okay, these many steps in the order of 1 by k sigma equals to 1 to L minus k delta sigma of I power minus 2 log of L by delta log of L square by delta sigma I plus delta power minus 2 sigma of L minus 1 log of L by delta log of L square by delta square sigma L minus 1. So this is the total number of steps the item is needed to click so that the process stops. So if all the weights are at least half with probability same as 1 minus delta, then we see that the number of steps will be taken as sigma equals to 1 to L minus 1 delta of sigma of I power minus 2 log of L by delta log of L by delta square sigma of I. Okay, so these two theorems have been used on the upper bound of the algorithm. So next, let's go to the next slide. Next is the lower bound. Lower bound we have theorem 2 in the lower bound. So T star is the optimal time complexity. When do we get the optimal time complexity here? We get this optimal time complexity when T star, this is the term optimal time complexity, that is greater than or equals to log of half in times 4 delta by mu k tilde. So mu k tilde is defined in the next set into sigma equals to 1 to k 1 by d of I to k plus 1 plus sigma j equals to k plus 1 to L 1 by d of j comma k. So what is mu k tilde? And this is less than or equals to minimum of 1 by w prime. W prime is the new weight and the total number of items k. So if we see here the upper bound, the expected number of observations of items per time step, use d of m comma n. So how do we see the upper bound of the expected number of items expected number of observations of items per time step? We see the distance. We'll see the KL distance between the W of m item and W of n item. So we somehow define the new distance called as KL distance, KL divergence, and d of m comma n equals to KL divergence of W of m comma W of n. So how do we define KL of P comma Q? KL divergence of P comma Q is defined as P log of P by Q plus 1 minus P log of 1 minus P by 1 minus Q. So this is the new distance we see to find the upper bound of the expected number of observations that we see per time step. So as we go into the next slide, we see the tightness of the bounds. Okay, the tightness of the bounds here are defined with as special case is that so 0 with 0 less than W prime. So we saw W prime is the W of L, the last item's weight, and W star is the optimal weight, and that lies between 0 and 1. The k optimal and L minus k suboptimal items have click probabilities W star and W prime respectively. Okay, for optimal items, we'll be having W star as a click probability, and for L minus k suboptimal items, we'll be having W prime as a click probability. So this is the tightness of the bounds of the click probabilities. And the next theorem we use here is corollary 3. Corollary. If the optimal click probability lies between 0 and 1 by k, the optimal time complexity is omega of L W prime square by W star minus W prime whole square with intersection of order of L by k of W star minus W prime whole square. If W star is between 0 and 1 by k, then we see T star belongs to omega hat of LW prime of 1 minus W star by W star minus W prime whole square with intersection of order of W star L by W star minus W prime whole square. So we see here the upper bounds above are achieved by algorithm 1, the algorithm we have been just seen before. These are the upper bounds that are being achieved by the algorithm 1. So as we go on to the next slide, we see the experiment that is being done in this paper. So on the x-axis, we have W star and W prime. W star is the click probability of the optimal item of k optimal items, and W prime is the click probability of the L minus k suboptimal arms. So on y-axis, we have average time complexity on the order of 10 power 4 or 10 power 5, 10 power 6. So if W star and W prime are between 0.45 and 0.05, we here see the descendant of ut of I comma delta. Okay, and we plot here of cascade band best term identification epsilon delta k model, and ascending of mu tilde mu cap of I, ascendant of ut of I comma delta, and lt of I comma delta, and mu of I descendant of ut of I comma delta, and lt of I comma delta. So when we see average time complexity, when we use cascade best term identification model, we see the less average complexity. Okay, so average time complexity is incurred by different sorting order of ST, ascending order of Ti of t. Ti of t is defined in the algorithm 1 of the order of mu t of I or ut of I and lt of I, with L equals to 64 items and k equals to 16 items, and the failure probability is 0.1 and epsilon equals to 0 in the cascading bandits. So we see this thing in this slide. So the next further empirical evidence in the experiment is that on the left hand side, we see W star as 1 by k and W prime as 1 by k square. W star is the click probability of the k optimal items, and W prime is this click probability of the KL minus k suboptimal items and average time complexity. And here the blue dots here are average time complexity in the graph, and the red line here defines the fitted curve that is being fitted in this curve, and the cyan or dashed lines will be are of 95% confidence interval. Okay, we have in confidence interval is being defined of LCB and UCB. So average time complexity is in the order of 10 power 5. So we have in the first graph, we have linear increase in the curve. So linear increase in the average time complexity. Cyan and dashed lines, 95% confidence interval in the second graph, average time complexity. Next, as this paper comes to an end, we go on to the next paper, paper 2. Paper 2 is cost aware cascading bandits, and this is paper 2. So we apply our knowledge of paper 1 in the paper 2, so that we develop the algorithm. We develop the algorithm. So what does this mean? Cost aware cascading bandits. Cost aware cascading bandits model is that we introduced a variant of the multi-armed bandits considering random costs associated with the pulling arms. Okay, this is the cost aware cascading bandits model. The next term is the sequential elimination examination strategy. What does this mean? Sequential examination strategy means the learning agent sequentially examines items until a stopping condition is met. So in this, we balance exploration and exploitation terms. The next is the objective. So what is our objective? The objective in this paper is in the cost aware cascading bandits is that we maximize the net reward, expected net reward in each step by optimizing the ordered list of the items and decide when to stop the examination. So when to stop the sequential examination strategy. This is our objective. We will be maximizing our expected reward, and we need to optimize the ordered list of items. The next term is the offline and online setting. What does the offline and online setting mean? This investigates the decision-making scenarios with known and unknown item state and cost statistics, covering a wide range of all the practical applications that is needed. Okay. The next is the optimal policies. What are the optimal policies we will be using here is that we identify the unit cost ranking with threshold 1, UCRT1 policy as optimal for the offline setting. And for the online setting, we use cascading upper confidence bound, CCUCB setting. So these are all the terms that are being used in the cost aware cascading bandits, so that we will be developing the model that we have been seen in the paper 1 of in the fixed confidence interval setting model. The next term is that regret analysis. So what do we mean by regret analysis? This analyzes the cumulative regret to evaluate the performance of the proposed algorithms in terms of suboptimality compared to the best arm. So this is meant by regret analysis. Next is a lower bound. This provides the theoretical lower bound for all the consistent policies, like establishing performance limits of the strategies we use, like decision making, like selecting arms, that is being used in the lower bound. Next is cost information availability. This differentiates between the scenarios like with implicit and explicit costs. So this is the differentiation between the scenarios of implicit and explicit costs, and this addresses the practical considerations in the decision-making process. The next term is that order optimality. This introduces CCUCB2. CCUCB2 we just saw in the online setting as order optimal when instantaneous costs of pulling arms are available to the learner. Then okay, these are all the terms we use in the cost aware cascading bandit setting. So by using all the knowledge we gain from paper 1, we are going to find number of samples required to find best arm with high probability. This is what we are going to apply in the paper 2, and that is cost aware cascading bandits. So this is being applied in our paper 2 so that we develop a model and we find the best arm with the highest probability. So this is the next what goal to us, so that we can get the best arm with highest probability. Okay, this paper like paper 2 is defined in this way. Thank you, and the end. Thank you so much.